and deals with samples. If you kindly turn to the top of 246, sample and distributions. Let's read this together. In previous sections, you studied the relationship between the mean of a population and the values of a random variable. We took the population mean, we took the population standard deviation. We put them into your z-score formula, we put them into the x, whatever. In this section, you will study the relationship between the population mean and the mean of samples taken from a population. Now, what happens here is, if you take a sample from a population and you base your whole study on that one sample, what if that was not a good sample? What if that really wasn't representative of your population? You did everything right, you surveyed, you did what you were supposed to, you found a way to generate random numbers, or whichever way you did it, if you did cluster, whatever you did. So if you're getting one sample and you're basing your whole judgment on your one sample, you can have an invalid sample, or a sample that's not quite so representative of your population. So in this section, what we do is we do multiple samples. And from those multiple samples, you take the mean from those samples, called the sample mean. And you can either use the population standard deviation, or you can use the sample standard deviation. Sometimes what happens is we still use the population standard deviation because that's been set ahead of time. Then our samples we just use our sample mean. Other times you're going to see we use the sample standard deviation with your sample mean. So in this section, we do this a little bit differently. We have multiple means. We take multiple samples and we calculate each one of those samples. We calculate a mean, and then all of those means together, we calculate your sample mean. And we write your sample mean like this: x bar. This means sample mean. So when you see an x bar, that's a sample mean. Okay. It's very different than what we've been doing. We've been testing your population, and we've been looking at your population, pulling out one random person, one x value, whatever x's we're looking at. Like if we did your tires, we checked one random tire from your whole population. So now we're going to pull out samples instead of that one random x value. And because that one random x value might not cut it in our real world. So we're going to pull out samples from your population. Now, when you do this, every sample has to have an equal chance of being selected from your population. And it has to have the same characteristics as your population. Rather than run your random variable x, we're going to run your samples through here. So we're going to gather more than one thing. You know how every time we check, we check one student, what's the probability of this person being less than this, greater than that, equal to this one or this one. So now we're going to work the same kind of concept, but we're going to do it with samples. And you should get a better feeling when you take multiple things out of your population. So when we do this, and the central limit theorem is one of the biggest concepts in statistics. We're going to study the relationship between the population mean and the sample means. The mean from all the samples we have taken. We're not just going to pull one random value from our population or one random sample. We're going to pull multiple samples. A sampling distribution, therefore, is the probability distribution of a sample statistics that is formed when samples of the same size n, are repeatedly taken from a population. In other words, here's the population of my class, 30 kids. I'm going to take samples of 5. Random samples. I find a random number generator. I pull out one sample of 5. I pull out another sample of 5. From my same population, all the same characteristics of my population. From those 5, I take the mean of whatever it is I want to see your grade average, for instance. Instead of pulling one random person and checking their grade average, I'm going to take a sample of 5, and I'm going to do multiples of them. I'm going to take their grade point average, and I'm going to average it in with all the samples that I have. So you're repeatedly taking this from the same population. A sampling distribution of sample means says if the sample statistic is the sample mean, oh, it's on the other page, then it has these properties. I should have put those together. So it has these properties. The mean of your sample means is equal to the population mean. Eventually, your mean of all your sample means will equal the same as your population. Eventually. The standard deviation, however, is the one that changes. The standard deviation, you know how we do your z-score formula like this? Right, we're still going to use this. We're going to use your sample mean this time, but this is the guy that's going to have to change. The standard deviation is equal to the population standard deviation divided by the square root of how many are in your sample. So your sample standard deviation is going to change in this. This is the only one that's going to that you're going to see a big change in. So you're going to have to know, when am I doing my sample mean versus my population? And you can usually tell by, they'll tell you, I took sample size 25. Whenever you see an N for your samples, then you'll know that you did sampling. The standard deviation of your sampling distribution of the sample means is called the standard error of the mean. This is something else that you're going to see used, the standard error of the mean. Okay, that's your same as your standard deviation, but these are for your samples. So it's kind of confusing right now, but once we start working with this, it'll hopefully fall into place. What we did before was a population. We checked one thing against your population, took a random person, took a random set against your population. This time, we're taking multiple samples from the same population, and we're taking each mean and then the mean of all the samples together. And that's what we're going to compare to. That should kind of give you a better, a closer to being more reasonable through this. Okay. I don't know what happened to my sample here. Okay, if you turn to page 247. This says this. It'll kind of show you how the population mean is the same as your sample mean, but your standard deviation is not. You write the population values. Your population that you can choose from is 1357. You write them each on a slip of paper and you put them into a box. You randomly choose 2 slips of paper with replacement. Replacement means you're going to bring it back to where it was and pick more samples. You list all your possible samples of your size equal to 2, because you're only picking 2. Then you calculate the mean of each one. These means form your sampling distribution of your sample means. You're going to find the mean, the variance, and the standard deviation of your sample means. And you're going to compare it to the mean of the population and the standard deviation. If I took this and I put this in my L1, I would come out with the mean, which is equal to my population mean of 4, and I would come out to a variance of 5, and my standard deviation would be radical 5 would be 2 point something or other. Okay, that would be from my population. Now, my sample is this. If you take a look at what they did in the chart, and I'll work the chart out if you need me to, but if you can see their chart, they took all the possibilities of 2 things. In other words, I'm going to add all the ones. 1, 1, you're doing replacements. So 1, 1, 1, 3, 1, 5, 1, 7. Okay, see that first part? Then they did it with the second number. They did 3. 3, 1, 3, 3, 3, 5, 3, 7. See where these numbers are coming from in your table? You with me, guys? I know this is kind of tough to get, but just kind of hang in there. Once we prove that this works, then we use the concept. So we just got to get through this today. Then we do the 5. 5, 1, 5, 3, 5, 5, remember you're replacing, and then a 7. Okay, they added them together, divided them by 2, because you have a sample size of 2, and they found your sample mean. So they said 1 plus 1 is 2, divided by 2 is 1. 1 plus 3 is 4, divided by 2 is 2. 1 plus 5 is 6, divided by 2 is 3. See it? They came up with your sample means all the way down. Stay with me. These are your sample means. This is your sample. Sample of 2. That's your sample of 2. So they came down, all the way down, and did the right-hand side of your table. Now, from that, they had all the 16 samples of size of 2. We could take that and stick this into your L1. We can stick this whole thing into your L1, and we can do a one-verse stat and find your sample standard deviation and your sample mean. So they did it for us, and they found that your sample standard deviation, your sample mean is the same, but your sample standard deviation is slightly smaller. Okay, so if you take a look down there, they took n, which is 2. You with me? Here's your standard deviation. They took your standard deviation over the square root of n. N is 2. And when they do this, they had a sample standard deviation of about 1.581. Your population was 2 something. So if you put this in all of these into your L1 and you did a one-verse stat, your mean is still going to come out to be 4, but your sample standard deviation is going to come out a little bit different because we're using n of 2. Yes?
Do you put it in L1 and L2 or just in
No.
L1, 1, 1?
No, this one you can't put this in. You can put in these in your L1 as your population, these 4, and find your population information. When you do your sample means, you just put this column in. All through your L1s.
So you have to write that column and figure it out?
You just do it in the L1 table. Just go to L1, do L1, just say 1, 2, 3, whatever the rest of their things, and then just do a one-verse stat on L1, and you'll come out with this information.
But to get those numbers, like you have to do the table.
Well, you have to figure out every possibility here. Like it's like a tree. Here's my 1, my 3, my 5, my 7. I can pick a 1, a 3, a 5, a 7.
So what's the last
A 1.
one?
So these are the averages, the means. So you did 1, 1, 1, 3, 1, 5, 1, 7. See this part right here?
Oh.
See this part? This came off of your tree because your problem said with replacement. Then we took the mean, the average. We added these two together, divided it in half. So you keep doing this. 4, 2, 6 is 3, 8 is 4, 10 is 5. See how we're getting these? 6 is 3, 8 is 4.
All those numbers?
These are all your sample means.
So we should write that table like.
No, you shouldn't write it. I just want you to see the difference between taking a population, taking a sample mean.
So we won't have to figure out.
You'll never have to figure any of this out. But it's just like a good way to say, where did this sample means comes from? These sample means came from one population. Your population only had 4 numbers in it. But we were going to choose samples of 2 and randomly select them and put them back, replace them, so that from our tree, these were all the possible things that could happen. Then we took the sample means of those pieces of your sample of 2. From there, after we took your sample means, we put them in your calculator and we figured out what your standard deviation would be. Your mean is going to come out the same. If you added all of these pieces up and you divided by 16, your mean would come out to be 4, which tells us that your sample mean is the same as your population mean. What's going to be different is your sample standard deviation. That's going to be this formula. That's a new formula for us. Anybody want to put this in your L1 just to check it? for me? If anybody wants to be daring, put it in your L. Who did it? Put all this in your L1 and tell us what you get. This is a good way to do this. Go ahead, everybody put it in your L1.